formula that you have to memorize. Yay! That's good. You'll always be given a formula, and actually we already have run into one example that used a law of cooling formula. I only remember because I remember, Nathan, you had said something about the room temperature. We talked about the cup of hot chocolate or something being left on a counter. Do you remember that? And the cup of hot chocolate cooling down until it was kind of in unison with room temperature. And then it wouldn't cool anymore. It would just sit at whatever room temperature is. So this gets us into it by having us consider an exponential equation. Is this growth or decay? What did you say? Decay, because that's less than 1, right? What's my y-intercept? Think about parent graph a, b to the x power. Nope. 8. That's my y-intercept. Either you memorize it or you know you set x equal to 0, and anything to the 0 power is 1, and 8 times 1 is 8. So there's my y-intercept. Okay? And then 1 unit later, since I'm consistently multiplying by a half, what will the value be 1 unit later? 4. Let's see, 5 would probably be about there. 1 unit later, what would the value be? 2, because 4 got chopped in half again. 1 unit later, what would the value be? If I half 2. 1. Well, my scale's not very good, but we get the idea. We didn't need our calculator, that's foolish. Clearly the value of y is getting smaller as x gets larger. Does it ever reach 0? No, right? We talked about this already. Let's write this down just to practice this notation. As x approaches infinity, what does f of x approach? Or in other words, what are the y values approaching? As our x's are getting bigger and bigger and we move to the right, the y coordinates are approaching 0, but they will never touch it. Why or why not? Really because in exponential graphs, y equals 0 is an asymptote. So this is just an exponential decay parent graph. Quick review there. Now we have a liquid that's starting at a temperature of 200. So let's label this 200. And therefore halfway up would be 100. And it begins to cool in a room that is at a steady temperature of 70. So where would 70? This would be maybe 50, so 70 would be about here, right? That's room temp. So this cup of hot chocolate starts at 200. And we talked about, does it cool faster in the first minute? Or does it cool faster in the 60th minute? The first minute. Because the discrepancy between the temperature of the hot chocolate in the room is magnificent early on. So the bigger that difference, the more drastically it's going to affect the cooling. So it cools quickly at first, and then the rate at which it cools kind of lessens as we move on in time until that cup of hot chocolate's temperature really becomes one and the same with the room temperature. So this is like an exponential decay graph as well, but how did it get shifted? Up how many units? 70. So what was the y-intercept then before it got shifted up 70? I heard it. 130. It was initially, if I shifted everything back down 70 units, the y-intercept would have been 130. I don't really know the rate of decay to the t power, but I do know that there's this plus 70 at the end. So B asks you, why would this not model this well? Because the parent graph, y equals a b to the x, assumes an asymptote at y equals 0, and that's not what's happening here. Okay, so it would be because our asymptote is at 70 degrees, or room temperature. Okay? The only way for us to truly figure out, well, I don't even know if we can do that. Trying to think if we could write this equation yet with our skill set. Isaiah, what are you thinking? Well, there is a small technical. I was kind of waiting for that question the last time. We know in real life it will actually hit 70, but in this world, they're thinking it will be 70.00000000001, and then 2 days later it'll be 70 with a whole bunch more zeros and one. It will always be slightly bigger than 70, but for us in the real world, it's 70. So there is a little hiccup there. It gets infinitely close to 70, so it pretty much is 70 in real life. All right, so that's just the idea of Newton's law of cooling, which also can be Newton's law of warming up as well, but it's not really ever called that. All right, so here we're given a formula, and I'll tell you what all those variables stand for in a minute. After sitting out of the refrigerator for a while, a turkey at room temperature is placed into an oven. So this is going to be Newton's law of warming up. At 8 a.m., when the oven temperature is 325, Newton's law of heating explains that the temperature of the turkey will increase proportionally to the difference between the temperature of the turkey and the temperature of the oven, as given by this formula. So T is the final temperature, in this case of the turkey. T sub 0 is the starting temperature of your object, in this case the turkey. Any guesses as to what T sub A is? Nope, we have that. Final. It's just plain old T. Yeah? Yeah, kind of. In this case, it's going to be the temperature of the oven. It's the temperature of the space that is surrounding the object that's either cooling off or warming up. In this case, that space is the oven. So I would say maybe like the air temperature surrounding the object. So that, in this case, will be the temperature of the oven. In the previous case, yes, that would have been room temperature, the temperature of the space surrounding the hot chocolate. not exactly your rate, but it's the constant that ties in with your rate. We've dealt with K before when we did inverse variation. It was the constant of variation. And T, of course, is time. So this is telling us that the turkey reaches a temperature of 100 degrees after 2 hours. What was the temperature of the turkey at 0 hours? It's at 68 degrees, good. So where in this formula does the 100 go? Any ideas? Or where does the 68 go? 68 is definitely T sub 0, the initial temperature. Is 100 degrees, that's obviously a temperature, right? Is that the temperature of the space surrounding the object, or is that the final temperature? Final. At least for these 2 hours it is. So this is capital T. 2 hours is lowercase t for time, not temperature. Find the value of K, so we're obviously looking for K. So we have capital T is 100. What is the air temperature surrounding the object? 325, that's the oven temperature, that's T sub A. T sub 0 is 68, minus T sub A gets used again, e to the negative K times 2. Now, what can we do to clean this thing up first? Parentheses. So 68 minus 325 would be a good place to just clean up. We're not really solving yet. It's plus negative 257, right? So it's technically minus 257. And then the exponent is just negative 2k. Now I'm en route to solving. What do I need to get rid of first? 325. Subtract 325 from both sides. Here's what you do not do. I do not do 325 minus 257. For the same reason, you don't need to write this down. I should never subtract that 257 from that 325 when there's an x attached to it, correct? So don't make that, it's a little bit more tempting here because the x isn't that obvious, but you cannot do that. So we're just going to subtract over 325, which is going to make negative 225 equals negative 257 e to the negative 2k. Followed by, not ln yet. E has to be all by itself for the ln. Jake? Yep, divide by negative 257, so I'm just going to do that. Now natural log both sides. So when I natural log on the left, natural log on the right is going to cancel that. I'm just trying to save space here. And then divide both sides by the negative 2. So k to the nearest thousandth equals the natural log of negative 225 divided by negative 257, close parentheses. Take that answer and divide it by negative 2. 0.066. Tenths, hundredths, thousandths, yeah. So So just like with direct variation and inverse variation, once you find that K, that constant of decay rate for a specific scenario, that's the K you use from that point forward. So now we have to use that K to answer a follow-up question. Determine the temperature of the turkey, so the final temperature at 3 p.m. So I'm looking for capital T. I'm looking for the final temperature. What's T sub A? Still 325. What's T sub 0? Still 68. That was at 8 a.m., right? That was the initial time that we started all this nonsense. 8 a.m. Minus T sub A is 325 again. E to the negative, K is 0.066. And what is the number of hours I'm waiting? 7. Very good. 8 a.m. is the frame of reference here when the turkey was 68 degrees when you were about to put it in the oven. We're waiting till 3 p.m. From 8 a.m. to 3 p.m. is 7 hours of waiting. So after 7 hours, the temperature of the turkey will be, now there's no solving here, this is already, the capital T is already by itself. It's just plugging this in exactly as you see it. Oh gosh, I accidentally hit another button. Negative 0.066 times 7, I hit a plus. Enter. 163 degrees. So I would assume the internal temperature of the turkey is 163 degrees. Bring it over. $325 plus 68 minus 325. You didn't put your negative on the K. The formula is a negative KT, so you forgot your negative. Yep. Bring it up. You may. You have the wrong exponent. It's negative 0.066, and you probably have 0, 0. You have an extra 0 in there. Okay, so calculator use is obviously important, so we want to iron out those wrinkles now, not on our corrections on a test or quiz. So go to exercise 3 on the back, which is going to touch upon that whole cup of hot chocolate cooling down piece. We're now going to model this cooling temperature using this equation, which we'd already begun to do, where A, B, and C are all parameters in the model. Which of these constants is 70? And we said C. So C is 70. Yeah, I do that. Isn't that weird? C equals 70. We already talked about that in the front. That's the... Now, none of these constants is equal to 200. And we kind of saw that. The 200, we had to think about shifting it back down, and we got that 130. But T of 0 equals 200. So if I know that when I plug in a T of 0, the temperature equals 200, I get 200 equals some A value, some B value, to the 0 power plus 70. What does this allow me to solve for? A, because B to the 0 is just 1. And then when we subtract 70 over, A equals 130, which we already thought about and came up with just thinking logically, but there's an algebraic reason. So in order to find B, we would need one more data point, and they give us that in D. They tell us that after 5 minutes, temp is 153. So 153 equals, our A value we know is 130, times some B value, to the T power, T is 5 minutes here, 5 minutes, 153 degrees, plus 70, and I would solve for B this way. Okay? Subtract your 70 over. Do it. Divide by 130.